So welcome to AQA AS 2017 paper 1. As per usual, I can't show the paper on screen, sorry about that. That's because AQA will get the channel deleted like they nearly did in the past. So let's start off with question 1. Deduce the name of particle X. Well, we know it's up, down, down. And if you see my videos, I call that the nud because it's what a neutron is. The nud and the pud. Proton is up, up, down. State the type of interaction. Well, it's either going to be weak, strong, or electromagnetic, but because we know there are leptons involved, it has to be the weak interaction. 1.3, what type of particle is W+? Well, it's what is carrying things, charge, momentum, whatever. It's the go-between particle. We call this you can call it a gauge boson or just a boson. The alternative name for it is an exchange particle. Either one of those is acceptable. So, how are charge and baryon number conserved? So Q and B. Got to talk about quarks. Well, let's have a look at charge first. We know that a neutron is turning into a proton, so that's up, down, down, going to up, up, down. So actually, in reality, we can forget about that and that. It's really just a down quark turning into an up quark. The charge of a down quark is -1/3. Okay, -1/3 E, but don't really care about that. And that's going to +2/3. Let's write out a formula for this. Down quark is going to up quark plus an electron plus an anti-electron neutrino. So the charge is -1/3 going to +2/3 plus -1 plus 0. So that all checks out. Baryon number. Well, we can think about it in terms of a neutron going into a proton. They both have a baryon number of 1, or we can just say, well, each quark has a baryon number of 1/3, and then electron and antineutrino have 0. So that works out as well. Like I said, you could replace those with 1 if we're considering the neutron and the proton instead of the quarks. What's the only stable baryon? It's a proton. Every baryon decays into a proton in the end. So muons are unstable. What does it turn into when it decays? Well, it's a lepton. It's effectively just a heavy electron. So it turns into an electron. So we have this graph. First of all, we're being asked about why is it like that for a filament bulb? Why does it curve over like that? So this is your stock question, and so you need your stock answer locked and loaded. It's very, very common. Every other paper has this question. First thing we say is that when electrons flow in a filament, they collide with the metallic ions, transferring energy to them, causing them to vibrate more. So we can say that's an increased temperature. This results in even more frequent collisions, which increases the resistance. So we can say at higher PDs, the effect of this is greater, therefore further increasing the resistance. Therefore, line is curved. So, what is the resistance of the resistor? Well, we have a nice straight line. Some people think that it's the gradient of the line that gives you the resistance. No, common misconception. All you have to do is pick a point and do V equals IR for that point. You will never find the gradient of an IV graph. You'll only pick a point and use Ohm's law. So therefore, resistance is equal to voltage or PD over current. So let's pick a point. The larger values, the better. I'm going to go with a PD of 6. Okay, 0.0. Divide that by, I think that is 0.42. That gives me a resistance of 14.3 ohms, but I'm going to give that to 2 sig figs. Seeing as none of our data went to 3 sig figs. So then we have the resistor and the bulb in series. What EMF is necessary to produce a current of 0.18 amps? Well, we know they're in series, so we need that 0.18 amps going through each one of those. So all we have to do is find out the PD required to push that current through both of those things. So for the resistor, I can see that is 2.6 volts. And for the lamp, just reading off the graph, at 0.18 amps, that is 0.8 volts. Therefore, the total voltage or the EMF required is going to be both those added up. It's 3.4 volts. Now we're told that they're attached in parallel. So what's the total resistance going to be? Well, as per usual, we're just going to use V equals IR. Don't forget that all of electricity just comes down to Ohm's law. It just depends what you're using it for. Are you using it for an individual component, a combination of components, or the whole circuit? Well, in our case, we're going to be using it for the whole circuit. So I'm just going to write down V tote equals I tote times R tote. And that's what we're looking for. So we know that it's 4 volts. So that's going to be 4 volts. So what's this going to be? Well, 4 volts. Looking at our graph again, I can see 4 volts with the resistor gives me a current of 0.28 amps, whereas the lamp, that gives me a current of 0.36 amps. Therefore, combining those two, we end up with the total current flowing through the whole of the circuit. So it's going to be 0.64 amps. Therefore, dropping the totes, resistance again, here's voltage divided by current. So that's going to be 4 divided by our 0.64. That gives us an effective resistance of 6.25 ohms. But being consistent with our sig figs, seeing that we weren't given data to a greater accuracy than 2 sig figs, we're going to go with 6.3 ohms. Okay, we have a resistivity question. Let's write down our data. Resistance of 14 ohms, length of 0.36 meters, diameter of 32 micrometers. We know we're going to have to find out the area from that in a second, and we're being asked to find out the resistivity. The equation is rho is equal to RA over L. So let's find out the area first. Best to do this one step at a time because this is worth a mark even if you get the answer for resistivity wrong in the end. So that's pi d squared over 4 if you have the diameter. Don't forget to actually write down what you're putting into your calculator, because people miss out on marks when they maybe put something into their calculator wrong. So they don't get any marks, but then if they actually write down the calculation with numbers, then you can get a mark. And we're going to go to 2 sig figs. That gives us 3.1 times 10 to the minus 8. And the unit, as per usual, is ohm meters, not ohms per meter. People often put that accidentally. Okay, bit of mechanics. We have lots of data about this wheelchair. We have a mass of 55 kilograms. We have a distance of 12 kilometers, so I'll tell you what, let's put that in standard form, 1.2 times 10 to the 4 meters. Oh, hold up, we've been told that we have a person in it that weighs 65 kilograms, so actually we're probably not going to need that, but rather the total mass. So that's going to be 65 plus 65, so that gives us 120 kilograms. We have a maximum speed of 1.5 meters per second. We have an EMF, or let's just put a voltage, of 12 volts. And we have a charge of the battery, 7.2 times 10 to the 4 coulombs. Okay, lots of data here. Could be a bit confusing as to what we're going to have to use. Okay, so we're being asked to find out what the power is, or show that it's around 100 watts. Now, power is energy divided by time, work done divided by time. Okay, but we don't really seem to have an energy or a time right now. But what do we have? We have voltage and charge. Now, you should know that voltage, just what the definition of it is energy per unit charge, or in other words, energy divided by charge, of joules per coulomb. So therefore, we can find energy from this, but then we need a time as well. Where are we going to get that from? Well, we have a distance and we have a speed. So speed equals distance over time. So we can use this to get our time. So we could do it all in one go, but let's do it step by step, shall we? So energy is equal to Q times V. So there's going to be 7.2 times 10 to the 4 times our 12 volts. And that gives us 8 point. Well, let's be really accurate with our workings out in the middle of our question. We only need to give our final answer to the right number of sig figs. So therefore that many joules. So we have our energy. Time, on the other hand, is equal to distance divided by speed. If we just swap round speed and time, need a little shortcut. So it's 1.2 times 10 to the 4 divided by 1.5. In other words, 2/3 of that. So I can do that in my head. That's just going to be 0.8 times 10 to the 4, or in other words, 8,000 seconds. So we have our time. Therefore, finally, power is energy divided by time. So it's going to be 8.64 times 10 to the 5 divided by 8 times 10 to the 3. Tell you what, let's get rid of some powers of 10. Why not? So 5 on top, 3 on the bottom, so that's just times 10 to the 2 on top. So in other words, 864 divided by 8. And oh, I think I can do that in my head. I think that's going to be 108 watts. However, our data has been given to 2 sig figs, so we have to make sure that our final answer is given to 2 sig figs as well. So we're going to round that to 110 watts. So a question with lots of different data, lots of different variables. We're being asked to find something. What did I do first? I wrote down the equation for the thing I wanted to find, and then I had a look at the data I had, figured out what I could find out with those things and see if those things fit into my first equation. Just a matter of keeping you cool and just maybe having a bit of a play to see what you come up with the data that you've been given, and then things will start to click. Next, we're being told that there's friction and air resistance. And we're told that all the energy in the battery is moved to use the wheelchair. Okay, so therefore we can say that the energy from battery has all been used to do work to move the wheelchair. So we can say that work done, or energy, is equal to force times distance. So we have an energy, we have a distance from earlier, so we can find out the force from that. Alternatively, the other version of this equation is power equals force times velocity. So we have a power and we have a velocity as well. So I'll tell you what, let's use this one here. Therefore, we can say that force is equal to power divided by velocity. So that's our 100, let's go with 108, divided by our speed of 1.5, and that gives me 72 newtons. If you'd use 110 watts, then you'd end up with 73 newtons, which is also acceptable. We now have a slope. Person in wheelchair here, and we're told that this angle is 4.5 degrees. So first we're being asked to find out the force that gravity exerts parallel to the slope. So we're being asked to find this force here. So forget about anything else, we're just being asked to find the force. Now you should know that that is mg sine theta, if the angle is the angle of the ramp. If you don't know where I'm getting that from, have a look at my easy vectors trick or forces videos. So we said we have 120 grams, that's a wheelchair and the person, times that by g, times that by sine of 4.5, and we end up with, to 2 sig figs, 92 newtons. Then we're being asked to find the maximum speed if the power of the battery is 100 watts. So the question is, what's the force that the wheelchair pushes with going to be? We already know we have this 92 newtons pulling down the ramp, but we're also told that the frictional forces are the same. The frictional forces are also going to be pulling backwards. Let's call that 73 newtons, seeing that that's what they like to use here. So I've drawn myself all the forces on the diagram. We know that at a constant maximum speed, the force pushing forward is going to be equal to the forces pulling backwards. So therefore, the force is going to be that 73 plus 92. That gives us 165 newtons. Now we can use P equals FV, rearrange that, power divided by force, so that's 100 divided by 165, and that gives us 0.61 meters per second. Okay, so what happens if you increase the mass or increase the speed? Let's go with mass first. Not the easiest thing to think about here. We are talking about level ground, so in an ideal world, the mass shouldn't affect it at all, because of course that only affects weight pulling downwards. But it will mean that more energy is needed to accelerate to that maximum speed, and that's due to F equals ma. More force, therefore more energy is going to be used to accomplish that acceleration. So we could say therefore the range is reduced. That's the main thing to go with. However, we could also say that in the real world, if a car is heavier, it won't go as far, and that's because it'll also increase friction in the wheelchair's mechanisms, or the bearings and the like. The more mass is pushing on bearings, then that means that the hotter they get, because there's more friction, so more energy is lost, so that will reduce range as well. Not an easy one to get there. So what about increasing the speed? The main thing is that this will increase frictional forces. We can say friction and air resistance. Therefore, more work is done against these. Therefore, this will reduce the range. Question 4 looks like we're looking at some Young's double slit, even though it's microwaves with an aerial. We have our diagram and we have our points. and we're told the distance from the two slits to that point D on the screen. So we're told that we have a maximum at all of these points, A, B, C and D. So what are we being asked first of all? Nice and easy. Why do we get a minimum between B and C and D? So we can say that between the maxima or maximums, there is a point where the two waves meet in antiphase, or we could say out of phase. Let's say 180 degrees out of phase. Destructive interference occurs and amplitude decreases to a minimum. Let's go one step further. Diffraction patterns is all about path difference. So let's say this is due to being of length n plus a half lambda. In other words, half and 1.5 wavelengths in our case here. Next we're being asked to find the frequency. Of course we're going to have to use the wave equation, are we? B equals f lambda or c equals f lambda. Do we know the speed? Yes we do. It's microwave, so same as the speed of light. What's the wavelength going to be? Well, let's have a look at our point D here where we have a maximum. We know the path difference at this point has to be 2 lots of the wavelength. In the middle, the path difference, PD, not potential difference, path difference here, PD is 0, and then here the path difference is 1 wavelength, so therefore it has to be 2 lots of the wavelength above. So we can say the path difference is equal to 0.723 take away 0.667, that is 0.056 meters. We know that that's 2 lots of the wavelength, so that's 2 wavelength, therefore lambda we can say is just half that, 0.028 meters. Therefore frequency, rearranging our wave equation, is speed divided by wavelength, 3 times 10 to the 8 divided by, tell you what, let's put it in standard form, 2.8 times 10 to the minus 2, so I can just put those on top there. So it looks like it's going to be of the order times 10 to the 10. That's 1.07 times 10 to the 10 hertz. But our data has been given to, oh actually it has been given to 3 sig figs. I think we can leave it as 3 sig figs for this one. But 1.1 times 10 to the 10 is also acceptable. Okay, so then we're being asked, why isn't it 0 at the minimum between C and D? Well, in order for waves to add up completely to 0, they must be identical and opposite. If we add those together, they make a flat line. However, because we have these two rays going different distances, one's going further than the other, which means that actually the intensities are going to be slightly different. So the one that goes a shorter distance is going to have a greater amplitude, and the one that doesn't go as far is going to have a lower amplitude, a lower intensity. If we add those up together, then we are still going to get a bit of a wave being produced when they interfere and reach the screen. So what we can say is that waves travel different distances, meaning their intensities will be different, therefore will not sum to 0 at the minimum. 4.4. The aerial is rotated through 90 degrees. Well, this is going to be polarization. We can say the waves are polarized. Could put in there plane polarized. Therefore, signal will decrease to 0 when turned through 90 degrees, as the waves will not be absorbed at that angle. Okay, we have this setup with aerial wire. What are we told? The area is 1.6 times 10 to the 5 meters squared. We're told the tension, so that's the force in the wire, is 5 times 10 to the 2 newtons. And we're given the Young modulus of copper of that many pascals. And we can see that the length is 12 meters. And we're being asked to find the extension. So let's crack out the Young modulus equation. If I want to find out delta L, all I have to do is swap them round. Let's cancel some powers of 10, why not? So we have on the bottom here -5 and 11. So actually, if we just take away 5 from 11, we end up with 6. And then we have 2 on top, 6 on the bottom. So therefore, we can take 6 away from the top. So we can say that that is times 10 to the -4 on top. Could cancel it down further with the 12 and the 1.2, but I'm not going to. And it gives me an extension to 2 sig figs of 3.1 times 10 to the -3 meters, or 3.1 millimeters. Okay, next we're being asked to find the tension in the wires there at an angle of that to the horizontal. So what do we know? We know there's 500 newtons pulling sideways due to the tension in the horizontal wire. This 500 newtons must be supplied by the angled wire. Let's just have a think logically. Is the tension in the angled wire going to be greater or smaller than that 500 newtons? In order to supply that 500 newtons, it's going to be greater. So T is going to be greater than 500 newtons. So therefore, if you don't know where I'm getting this from, have a look at my easy vectors trick video. We're going to take our 500 and we're going to divide by cos 65. We're dividing instead of timesing because we want a bigger number, and it's cos because the angle is between our two vectors. So we can say that we're sweeping through the angle. That's the way I like to say it. And that gives me 1,200 newtons. Okay, classic question. How are stationary waves formed? Easy peasy. We say that wind causes progressive wave on the wire and is reflected at the ends. These waves, now for some reason AQA love the word superpose, which is fine, but they don't allow interfere anymore, which is really dumb, but let's play their game. These waves superpose. Let's say what that means. Displacements sum. And we know that nodes must be produced at the ends, which determines what frequencies are allowed. So we're being asked to find the mass of a piece of wire. We're told the length is 1 meter. We're given the density of copper as 8,900 kilograms per meter cubed. So density is equal to mass divided by volume. Therefore, mass is going to be equal to density times volume. So therefore, we need a volume, we have a length, so we need the area as well. The area we were told was 1.6 times 10 to the -5 meters squared. So therefore, we can say that mass is equal to density times length times area. So we don't need that 1 in there actually. And that gives us 0. If we go into 2 sig figs, 0.14 kilograms. Next we're being asked for the frequency of the third harmonic. Well, let's go with the frequency of fundamental first, or of the first harmonic, because that's what we have an equation for. F is equal to 1 over 2L times root T over mu. Okay, so we saw the length was 12, tension was 500 newtons. Mu. What is mu? People often forget, but that is mass per unit length. In other words, kilograms per meter. And lo and behold, we've just found that out just now. 0.14 kilograms, okay, per meter. So that gives us a fundamental frequency of 2.47 hertz. So that gives us that. However, we're looking for the third harmonic, so that is that wave there. 3 times shorter wavelength, therefore 3 times higher frequency. So that gives us, after 2 sig figs, 7.4 hertz. Oh, what do you know, I've accidentally done 5.6 as well. We've been asked to draw the third harmonic. That's what it looks like. The number of the harmonic tells you how many loops are in the stationary wave. Why might the wire sag? Well, that's because the wire has deformed plastically due to high stress, therefore will not return to its original length. Random multiple choice question. It's not often you see this in a paper 1. What tells you that electrons act like waves? Photoelectric effect? No. That tells you that they act like a particle. Ionization? No. Again, shows you that they act like particles. Rings? Diffraction? Yes, of course. This is the main piece of evidence that things act like waves. Electrons and other particles, they act like waves too, but also just normal waves. We can tell that they're light waves because of diffraction. And line spectra, no, we know that's particle behavior as well. Speaking of line spectra, here's question 7. We have a discharge tube, we have a spectrum, and we have these 4 wavelengths emitted. And we're given the energy levels for the hydrogen electrons. So we're asked, what's the energy of the photon if we have the lowest frequency? Lowest frequency is least energy, because we know it's equal to HF, they're proportional, and also longest wavelength. And of course we know that from the wave equation there, they're inversely proportional. So if we're looking for the longest wavelength, that is 656 nanometers, or in other words, 666 times 10 to the minus 9 meters. We know that E is equal to HF, but if we have a wavelength instead of frequency, then we're going to replace that with hc over lambda. And of course that comes from the wave equation. I should probably put c in this case because we are dealing with the speed of light. So that's going to be Planck's constant times the speed of light divided by, let's put it in proper standard form, 6.56 times 10 to the minus 7. I can clear up some powers of 10, so minus 7 on the bottom, so that means we add them to the top, so let's say 15 on top, minus 34 and 15, that brings us up to minus 19. So that gives us 3 times 10 to the minus 19 joules, but we need it in electron volts, so just think, our conversion factor is 1.6 times 10 to the minus 19, but we want a bigger number because of course electron volts are smaller, so therefore to convert joules we're going to divide by 1.6 times 10 to the minus 19, and that gives us 1.9 electron volts. What is an electron like if it's at that level 0? Well, the atom has been ionized, therefore that means that an electron is free. Just note that we don't say the electron has been ionized, it's the atom that's been ionized, which means an electron has escaped it. 7.3, what about right at the bottom? Well, you should know that we call this the ground state. 7.4, why are energy levels negative? Well, that's a very good question actually, and not an easy question to answer because, well, it is just because we decide to put 0 at the top at ionization. We could put 0 at the bottom if we wanted to, but for the sake of consistency, we do it the other way around. So this is not a good question, to be perfectly honest. So we're just going to put something like energy is required to free electron. Okay, 7.5. This isn't a nice question either. So we're being asked to talk about how the tube emits EM radiation of specific frequencies. Let's deal with the high PD first. High PD is required to accelerate electrons through the tube. We can say from cathode to anode. Cathode being the negative electrode, anode being the positive one. So why is this? Why do we need electrons to move? Well, we know it's because if we have a discharge tube here, we have a cathode here, anode here, we have our gas atoms in here, an electron needs to barrel its way through and bash off and provide energy to the electrons in the gas particles in order for the discharge tube to work. So let's talk about that. Electrons collide with atomic electrons, transferring energy to them. These are raised to higher energy levels, and we could say excited. As they de-excite, fall to lower levels, they emit photons, the wavelength of which is determined by the specific drop in energy level. So by example of this, let's use the 600 nanometer wavelength as an example. We saw that gives us an energy of 1.9 electron volts, corresponds to drop, we can say transition to be posh, N3 to N2, because that's 3.4, take away 1.5. It gives us 1.9 electron volts. So there we go. Hope you found this helpful. If you did, please leave a like. And if you want to go on to paper 2, click on the card and it'll take you there. See you next time.